Okay, here's a quick video finishing off this lesson. So here's the example. Find the equation of the tangent line and the normal line to the curve of fx equals 2 tan x at the point where x is pi over 4. So to find an equation of a tangent on the calculator would be really easy. You would just graph this function and then you would press second, draw. So I'll show you on here. So you would graph the function in y1 and then you would press second, draw, which is where, second draw here, select tangent, number 5, and you've got to tell them at which point value of x. So you would type in pi over 4 and just make sure you're in the right, mode. Like in this case, you'd have to be in radians. And the equation of the tangent should pop up down the bottom. So see, they say y equals, basically that's y equals 4x minus 1.14 blah, blah, blah. But this would be non-calculator, so I'll show you how to do it non-calculator. So to start with, we'll find the equation of the tangent line, and then we use that to find the equation of the normal. The tangent is a line that just kind of represents the gradient at a particular point, and the normal is perpendicular bisect. The normal is perpendicular to the tangent and cuts at the same point, x equals pi over 4. So we're going to find the y coordinate first. So sometimes they give you the y coordinate, but they didn't. So we need a whole coordinate to begin with. So to find the y coordinate at this point, just sub in this point, sub in the x into here. So if you sub in y equals 2 tan pi over 4, you can use special triangles. Pi over 4 is the same as 45 degrees. 180 divided by 4 is 45 degrees. 2 tan 45. 45 degree triangle is 1 root 2. So the opposite over the adjacent would be 1 over 1. So tan 45 is just 1. So the coordinate is pi over 4 and 2. So that's our coordinate that we can use for x and y. Now to find the tangent, remember the tangent's a line in the form of y equals mx plus c. So we need to find the gradient, and then we're going to plug in the coordinate and the gradient to solve for c. So to find the gradient, we need to find the gradient function. So we've got to differentiate 2 tan x. So remember, the derivative of tan x is 1 over cos squared x. So the derivative of 2 tan x will be 2 times 1 over cos squared x, which is 2 over cos squared x. And that's in the formula booklet, the 1 over cos squared x. So find the derivative. To find the value of the derivative at x equals pi over 4, sub in pi over 4. So we've subbed in pi over 4 here. Remember, cos squared x means cos x squared. Cos pi over 4, see pi over 4 is 45 degrees. Cos of 45 is adjacent over hypotenuse. So cos of 45 is 1 over root 2. So I just replace this here with 1 over root 2. So 2 over 1 over root 2 squared. Square this, you square the top, square the bottom. 1 squared is 1, root 2 squared is 2. So it's 2 divided by a half, which is the same as 2 times 2 over 1, which is 4. So our gradient for our tangent is 4. So far we have y equals 4x plus c. And now we're going to use this coordinate and sub it in and solve for c. So sub in y is 2, sub in x is pi over 4. We know the gradient's 4. 4 times pi over 4 is just pi. So the value of c must be 2 minus pi. So that's just a number. But if you type in 2 minus pi in the calculator, you would get that minus 1.14 number. That's how they got that one. But it's non-calculator, so you would just leave it as y equals 4x plus 2 minus pi, and that's your equation of your tangent. Now you had to find this first to find the normal, because remember the normal is perpendicular to the tangent, so the gradient of the normal will be the negative reciprocal of the gradient of the tangent. So the gradient of the normal is the negative reciprocal of 4 in this case. So the gradient of the normal is negative 1 over 4. So far we have y equals negative 1 over 4 x plus c. And then to solve for c, we use the same coordinate because the tangent and the normal pass through the same coordinate. So plug in x is pi over 4, y is 2, negative 1/4 times pi over 4 is negative pi over 16. To solve for c, you would add pi over 16 to both sides. So 2 plus pi over 16 gives you a value for c. So our equation for this one is y equals negative 1/4 x plus 2 plus pi over 16. And that's the equation of your normal. That's how you do it all by hand. The tangent, as I said, if it's with calculator, you can do it on calculator, but the normal you have to do by hand. There's no way to do the normal on calculator. Next one, use the second derivative test to find the x-coordinates of the relative extrema, like maximum, minimums, that kind of thing, of fx equals a half natural log of x plus cos x over the domain 0 to 2 pi. So of course it's in radians. So have your calculators out and make sure you put your mode into radians. So first thing we need to do the second derivative test, you need to find the first derivative and then the second derivative. So the first derivative of 1 over fx, so remember the derivative of ln x, if you put that into, look in the formula booklet, it's 1 over x. So the derivative of half ln x will be half times 1 over x. Half times 1 over x is 1 over 2x. And the derivative of cos x is negative sine x from your formula booklet. So that's the first derivative here. The second derivative, we need to differentiate this one. So that's like the same as saying a half times x to the minus 1. So a half times x to the minus 1, if you differentiate that, negative 1 times here, so you get negative a half out the front, and then you get x to the negative 2, which you can express more elegantly as 1 over 2x squared. So, so it's kind of like saying 1 half times negative 1 over x squared, because if you differentiate 1 over x, that's x to the minus 1, differentiate that, you get negative 1x to the minus 2, which is this, and then it's a half times that. So that's why this one, when you differentiate it, becomes this one. The derivative of sine x is cos x, and so the derivative of negative sine x is negative cos x. So we've got the first derivative and the second derivative done. Now we've got to use them to find the relative extrema. So first of all, use the first derivative to find the x-coordinates of any critical points, like maximums or minimums. Because remember, at the maximum or the minimums, the gradient's equal to 0. And this is probably an easier one to solve with than that one. So let's just sub in that this gradient is equal to 0. The gradient function is equal to 0, and we're going to solve for x. Because it's with calculator, that's a pretty tricky one to solve with. I would just graph this, graph it in y1. So graph this one in y1, graph 0 in y2, and you'll get the function. Here's the green function, and here's the straight line through y equals 0, and find where they intersect. So they intersect at 2 spots, so you'll go second calc intersect, enter, 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 get this one, second calc intersect, enter, 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 and you get that one. There's your 2 values. So there's going to be, so on the original function, there's going to be maximum or minimums at these points. We don't know whether they're the max or min. But we can use the second derivative test to see if this one's a maximum or a minimum, and do it again to see if this one's a maximum or a minimum. Because remember, at a maximum, it's frowning. So at a maximum, the second derivative is negative. At a minimum, it's smiling. So the second derivative is positive. So sub in these 2 values into your second derivative, see if the answer is positive. If it's positive, you know you've got a smiling minimum. If it comes out as being negative, you know the original function had a frowning maximum. So second derivative, here it is. Plug in, so plugged in the number that we got over here. So plug this number into there, into my calculator, and I got this number. I don't have much space to show the subbing in. And then I plug this number into the second derivative, and I got that answer. So notice one of them came out negative, so the negative one means it's a maximum. The negative, so it's frowning, it's a max. If the second derivative comes out as positive, it's a minimum, smiling. So they want to find, it just said find the x-coordinates of the relative extrema, comment on whether it's a minimum or a max. They're the x-coordinates. So you could always check by graphing the original function. So if you graph the original function, so I've graphed the original one there as well, double check. Yep, it's a maximum here and it's a minimum there. So we were correct in our assumption. And thank you, and that's the end.